bicycle safety is still a challenge. There was a high increase in the mobility, especially during the COVID and after that, but to this growth of numbers of users, especially in Europe, there was also an increase in the number of fatalities. In Europe, the fatality the rate for cyclists is the only mobility system in the city that showed an increase in the numbers in the last years when compared to the other modes like motorcycle, pedestrian that are also vulnerable, and cars. And there is also another reason that needs improvement in safety, because the perceived safety of the users the perceived safety of users is a constraint in the use of bicycle for mobility. So improving safety is necessary for safe lives, but also for promoting cycling as mode of transport. We've already talked about traffic conflict as a surrogate measure of safety to supply the lack of crash data and mainly to have a proactive approach in safety. This application is more important for bicyclists because there is not only a problem of data collection, but also a huge problem of underreporting. Also countries like Sweden, where are a great care in safety of cyclists, has identified about 80% of underreporting of low severe injuries by bicyclists. Therefore, traffic conflict is a usable technique. But how it is applied? Also, in the previous session yesterday, Tarek showed some application of pedestrian tracking made by video cameras. No, on the Okay. On the right side, you will see the framework of in the recent paper from Tarek, from the video footage, camera calibration. So it is a very established techniques that give reliable results. But there are some also problems. One is related to the privacy, especially in Europe. Our GDPR has a strictly limitation in the sharing of frames collected by cameras. They can cover only fixed position, limited to the field of view of the camera. If we use a mobile system like drones, there are also safety problems. Again, in Europe, there are severe restrictions in the flying of drones in urban area. Therefore, we proposed an alternative approach that make use of simple sensors on board of the bicycle or also of scooters. We developed a data logger that is able to collect data from different sensors, mainly GNSS coupled with inertial measurement unit, but also other sensors for biomedical parameters like EEG, eye tracking, but today we will focus mainly on GNSS and inertial measurement unit. So the aim of the work was to define a smart device for data collection, to exploit the deep learning application for analyzing the rider behavior of bicyclists and to identify any anomaly conditions that can be associated to an evasive maneuver, and to identify black spots as location for that are accident prone in the road network. That is the general framework of our model. We have not time to go in detail of each step of the process, but we will focus mainly on the data acquisition and the model synthesis and results. In terms of data collection, we applied we use data collected by a GNSS sensor, but recording not only the position, as it is usual in this application, but the full string that includes also the speed and heading of the sensors, and of course also of the vehicles, because these data are more accurate than what can be obtained by analyzing the position only. You will see in the table, as for speed heading, we have a very good accuracy, less than 0.1 kilometer per hour and 0.0 degrees. Another relevant point is that the system acquired data at 10 Hz. That means that we collected 10 values per second. That is relevant because we realized during the research that an evasive maneuver of bicycle occurs in a time that is between half second and 1.2 seconds. Therefore, we need a very detailed tracking of the trajectory to identify any deviation from the normal, even swerving or any braking that can occur in less than 1 second time. We have also cameras just for recording the scenarios surrounding the bicycle. We applied the convolutional neural network as a deep learning technique because in other applications it showed good performance for handling time series data, heterogeneous data. It was robust in the identification of anomalies, even if in other field of application. It is suitable for transfer learning application, and therefore was selected as a good model, but we are now trying also a different model like long, short-term models, but we will talk today about the convolutional neural network, and specifically of convolutional autoencoder that consists mainly of two components. An encoder that reduces the dimension of the data, and a decoder that, based on the trained model, reconstructs the original data. This is the flowchart of the process. The data are transformed to be analyzed by the model from the multidimensional to one-dimensional string. The model has two layers in the encoders and two in the decoders. We will see that is relevant for the transfer learning technique as well. And the model reconstructs the original data. The validation was done comparing the input with the output. That means that based on the specific data of speed, heading, acceleration, swerving, the model expects some results. If the results are different from what happened in the reality, we can assume that something happened. There was an anomaly in the driver behavior because the model is trained to what we can call normal riding behavior. So the mean absolute error between what is recorded and what is reconstructed by the model is a measure of anomalies. I talked about unsupervised deep learning. That means that there is not a need of any labeling of data, and the model is trained without, it is not a classification model, so it is trained without any previous labeling. But for validation, we have labeled some of the data recorded. We shared the videos, the speed profile, the hidden profile with the panel of experts. There are 5 colleagues that helped us in analyzing the data and to identify any traffic conflict and also to define the severity of the conflict. It was a 2-round process based on the Delft technique. After a first evaluation of the results, the overall scoring of the expert was shared in the panel, and therefore they were reviewed their previous definition, reaching a very good agreement at the end. Therefore, the labeling was very consistent. Here we see some results. The blue line reports the mean absolute error, the difference between the input and the decoded data. When the values are over a threshold, which was identified, we can assume that there is an anomaly. Therefore, means positive results in the detection of anomalies. There are the red box. In the orange box, there are reported the actual anomalies. Therefore, when the prevision is consistent with the reality, we have a true positive, while when there is a detection in a position without a true positive, we have a false positive, while false negative means an actual traffic conflict that was not identified by the model. To analyze the performance of the model, we applied the classical confusion matrix, comparing true positive, false positive, true negative, false negative, with the performance indicators that were known of precision and recall, and also the F-score. Here you will see the results, but there are different model settings, but I will comment only the best results that are in the blue box. You will see that we reached a precision and recall of about 80% and a F-score of 77%. That was higher than with other traditional techniques like the principal component analysis that you see was lower than 50%. And it is interesting also higher than the more traditional approach that uses the threshold in the acceleration to identify traffic conflicts. You will see in the last row that also checking different deceleration rate, the precision and recall was never higher than 30%. Therefore, our model performed better than other more traditional techniques. Here you will see an application of the model where the clustering of position where there was detected anomalies can be mapped in a map, and it's possible, I don't know if the pointer works, no, okay. On the right upper side, there are some clustering of green dots that are localized at the termini of the bicycle track that go close to the sea. In the bicycle tracks were not any or very few anomaly detection, that was to be expected. There are another clustering in the center down part. You will see there are some green dots in the roundabouts, and also in the horizontal line that is a bus lane shared between bus and bicyclist. Especially the cycle track and the bus lane was used for analyzing the transfer learning capabilities. Transfer learning is a technique that used a pre-trained model to adapt the model to new data, new user, in our case on new road environment. It is a very efficient technique because it reduces the needs of data, the training times, that can be useful when you think to apply a model like I am presenting today to a huge number of users. Now we can think of thousands users that will share this type of application. We consider two different scenarios. One is transferring the same model to different users, but in the same road environment. For example, the model trained for one user in the bike lane can be transferred to other users that ride in a bike lane, separated bike lane. Or a model trained to one user in one road environment to the same users but to a different road environment. For example, the model trained to the user in a bike lane transferred to the same user but in a different road environment, in our case study in the bus shared lane. Transfer learning means that after first training, some of the layers are frozen. We frozen the outlier in the encoder and decoder part of the model and tested these two different scenarios. Here are the results. The orange line refers to the benchmark case. That means the model trained and tested on the same data. That is the best that we can have. The blue line is the previous presented model. Therefore, a model trained on one user and on one road conditions, tested on other data but of the same user and same road conditions. You will see that So the blue line is the case one that I have just mentioned. In terms of transfer learning, the best results are reported in the red line, that is named the case 4 in the slide, that refers to a model that was trained to one user in one road condition, transferred to the same user in the different road characteristics. So from bike lane to bus lane or vice versa. You will see that the red line is close in terms of mean absolute error to the orange and blue. Worst case are case 5 and case 3 when we tried to transfer a model. So the blue line is overlapped to the green. So different users, transferring the model between different users or between different users and different environment. Therefore, the main conclusions is that data partners recognized by the outer convolution layers are more specific of the user rather than of the road environment. That means that behavior is more related to the rider than to the road conditions. Each of us, when cycling, has his her specific riding cycling behavior that change no more in different road conditions. But different users have different behavior, so the model needs to be adapted to each user, while can be transferred for the same users in different road conditions. Here are my lesson learned that we would like to share with you. Again, micromobility is healthy, sustainable, accessible. The cost of vehicle is very low, but also vulnerable. We need to protect these users. Machine learning applied to data collected on board, identify traffic conflicts that are behavior in all the bicycle network, not only in limited location, by has to be done by camera and onboard sensor can work together, and we are working in this direction in our projects, and deeply eliminate the needs of labeling, and therefore can be effective in modeling the rider behavior, also based only on GNS data, but we need good quality in GNS data. That means high frequency data. You know that the standard smartphones can collect data usually at 1 Hz, so 1 position per second. That in our experience is not enough, but it can be increased by coupling the GNSS sensor with inertial measurement units that use acceleration, rotation in the three-axis to increase the accuracy and also the frequency of the data. Transfer learnings can considerably reduce the data and computation time requested, and can also open the way to innovative application of networking learning, for example, federated learning or gossiping, that make possible to share the model between different users and different road conditions. But I would like to conclude my presentation pointing out that artificial intelligence application in road safety is a multidimensional domain. We work together. I am a road safety expert, but we work together with computer science expert and also social science expert, because we need to understand also the acceptability of these systems. Therefore, there is a need of cooperation between different fields of expertise. That is my last slides, and thank you for your attention, and greetings from my town, Catania, Sicily, in Italy.
Okay. Thank you, Professor Cafiso. Because of the shortage of time, we started a bit late. We'll keep all questions to the question sessions. And I would like to call the second speaker, Professor Simon, to present his own work.
To switch on your microphone?
Yep.
Yeah.
Good morning, everyone. I guess I'd first like to start by thanking everyone for the invitation to come and talk to you today. I am going to focus on a number of opportunities, and I think when I was looking at what I want to say to you today, I looked at your ambitious Saudi Arabian vision achieved for 2030, which is a 50% reduction in crashes. And so I've geared my entire presentation to try to lay out what I think you can do to achieve 50% reduction in crashes. And I think you're all aware that you're not the only ones grappling with this issue. Cities around the world are asking the same exact question. Most cities and states around the world have adopted a Vision Zero plan, which is trying to target zero fatalities and serious injuries on the roads, on their networks. So how do we achieve this? So what I'm going to lay out for you, because you aren't aware of who we are as Advanced Mobility Analytics Group, so I'm going to tell you a little bit about our company, what we're doing, and I'm going to focus on how can you achieve the Saudi Vision 2030. I'm going to lay out a roadmap of how you can actually achieve that using video analytics as part of that solution. I'm going to talk a little bit about the foundations of video analytics. I think some of the previous speakers have talked about this. Tarek Syed spoke a little bit about this in the first session yesterday, but I'll recap some of those major points. And then I'm going to talk to you about how we tackle road safety from both retrospective and real-time solutions. How do we intervene in a continuous real-time basis, and how do we actually use information or data to make better decisions about how to invest in our network to prevent future crashes. And then finally, I'll walk through a few case studies that we've delivered for existing customers to help them answer these same questions, which is how do they reduce fatalities and serious injuries. So just to start, AMAG was founded 4 years ago by 3 co-founders, and in fact, Tarek Syed is one of the co-founders in the company. And essentially what our focus has been is commercializing or turning into, say, university-based research, the video analytics or the conflict analytics kinds of technologies that has been built and developed in the research world into commercial products that can help customers achieve goals that they set for themselves. And so Tarek Syed, myself, and Shimal Haq, both all based in universities, formed the company 4 years ago. And looking at us today, we're about 32 staff across 3 countries. We are plan to grow quite significantly in the United States next year. We have 3 products that I'll talk to you about. I'll talk to you about only 2 of them today, but and how those products and the technology behind those products that help us and help our customers to achieve reductions in fatalities and injuries. So essentially what we do, if you look at this diagram, we work with our customers who have video cameras installed around their networks or put up temporary video cameras. Most governments have access to video cameras that are monitoring traffic. So we use those assets, those existing assets, to convert that information into much more useful and reliable information to help us prevent crashes. We also process LiDAR information. As you all know, LiDAR information has some qualities different than video. Video is really, really strong at identifying and classifying objects. LiDAR is really, really strong at good distance estimation and 3D point cloud characterization. So when you combine those technologies, you get a great outcome. So we ingest that information, the video information from our customers. We will process that using AI, and a lot of the previous speakers have talked about AI and the powers of AI. I'll show you a little demo of some of these, the benefits of AI. We process that AI, and then we return that back to our customers via a software. And the software then enables the customers to go in and look at all the kinds of deep insights that are happening on the road. Speeds, flows, critical conflicts that I'll talk about and focus on for a fair bit of the rest of the presentation. So architecturally, this is what we do, and this is what we've set up with our customers. So there's two streams of flow. If you look at this diagram, there's sort of the red arrows, which depicts the real-time analytics product that we've developed. So if you start from the camera in the upper left, or a LiDAR device, we've got a camera or LiDAR device that we put up at a location. Typically what we're monitoring are complex locations on the network. So one of our customers, the city of Bellevue in Washington, did some analysis of their network and determined that 80% of their serious crash risk and injury problems occurred at only 20% of the locations. So effectively that means if we put up video cameras at our most complex sites, then we can actually tackle a large amount of the safety problem in any region. So we put up cameras. We use fixed cameras or permanent cameras or temporary cameras with our customers. And then we will process that through an edge device. And that edge device allows us to do the analytics in real time to measure what's happening right now at this very moment so that we can let our customers understand what's happening. And I'll give you examples and talk you through that. So that real-time feed then goes to other devices like traffic control devices. Hello? So that real-time feed goes to traffic signal controls, to I'm not sure why this is going on and off. So from the edge device, we can communicate with various in-field devices like traffic control, flashing beacons, and other examples. And I'll walk you through a few case studies to show you how we do that. And then the metadata also goes to a cloud environment that customers have access to. The blue area shows the more post-process, where we'll collect data, analyze it for our customers, and send it back to them. And it's not a real-time kind of delivery. Well, I can't see that. So what you see here is our sort of an image of our real-time product. And how this is helping customers is what I want to show to you. So what you see in the upper image is our video camera installed at a location, collecting real-time information. So what you don't see in that image is that the AI is running and is collecting all the information about all of these vehicles, their position, what kind of road user they are, how fast they're going, and importantly, if they're getting involved in conflicts with other road users. And what you also see in that diagram, and it doesn't display very clearly up there, but we're ingesting the traffic control information. So we know when the traffic signal is turning red, amber, and green, and we know when the pedestrians have walk signals and things like that. So that's part of the ingestion and allows us to deliver better analytics. What you get on the bottom, and we deliver this and produce this in real time, is our conflict heat maps. Those those heat maps, I'll talk a little bit about conflicts in a second, just to remind you. But conflict, those are really showing where all the near misses are occurring at that site. And where you see in the red zone on that diagram are telling us where, spatially where, and temporally where road users are almost hitting each other. We could even filter that map by delta V. For example, what's the closing speed of those vehicles or those road users to try to estimate the severity of those conflicts. Just finishing up about the company, these are some of our customers. I won't spend a lot of time on it, but we are in 6 countries, and we're solving these exact same problems that you're grappling with for our customers in other countries and in other cities. We also use a lot of partners to go to market, and depending on where we're working, we partner with other firms and technology companies to deliver our solutions to customers. On the far right, you'll see we have the 3 products that I talked about. I've been talking about the real-time product and the safety product, and I'll give you a few case studies of how those work. So, how does Saudi Arabia deliver on its promise to reduce 50% crashes over the next 5 years, 10 years? One of the ways you do that is by converting from this reactive safety approach on the right-hand side, which is reliance on crashes, to this proactive approach, which is reliance on what are known precursors of crashes or conflicts. And AI, which delivers all kinds of other benefits besides conflict analytics, and I'll give you a sense of that. Really, it's that transition from the reactive to the proactive and all the benefits that come with that will enable you and many other cities around the world to head towards and reductions in serious injury and crashes. The first one is better understanding of what's happening at these high-risk locations. Everyone in this room would be aware, probably many of you in this room are aware of what sites are really problematic, which sites are causing or the locations of most serious crashes and injuries. However, it's my experience that when I go talk to these cities and they show me their top 10 worst sites, for example, if I ask them what's wrong there, what do you need to do to fix that location, oftentimes they don't have a detailed understanding of what's happening. So one of the objectives is to understand in detail or diagnose the risk at those locations. The second one is, how do we mitigate risk in real time? How do we use technology to identify a risk that's unfolding right at the moment and mitigate that risk? I'll give you an example, a wrong-way driver. In the United States last year, they had 1,500 fatalities associated with wrong-way driving. How do you use a video analytics technology to, say, detect a wrong-way driver, send messages to flashing beacons, contact law enforcement automatically, and try to mitigate a potential disaster that might unfold from a wrong-way driver? As one example. The last area of investment is to look at rapid assessment of countermeasures. A lot of governments are very interested to know how effective a new treatment would be on preventing future crashes. And it's very difficult to assess that with crash data. So we can use conflict data to help us understand. The core of this is the fact that we use conflicts rather than crashes. And I won't spend a lot of time on this because some of the previous speakers have talked about this, but I will say a couple of things. If you think about the profession in the world, the last 50 years, we've been focused on measuring exposure, or how many users attend a site, to understand risk. That has been the best predictor of future crashes, is just how many people are using, how many cars go through on a day. And Teresa had made this point yesterday. We've been using these very highly aggregate methods to look at how many cars use a site over a given year, or an average day. And it's very imprecise. So the way to think about it is that if we can measure critical conflicts, that vehicles or road users in near misses situations, if we can do that objectively, that is the single best predictor. If we can measure that, it's the single best predictor of future crashes. There's nothing else that we can measure that does a better job of telling us what future events will happen at that location. And that's why we measure it. And if we discover in the future a better measure, we will use that. But right now, critical conflicts are the best thing we have to understand risk. So when we see risk, excuse me, I'll go back. I'm not sure how to get that video to play because it seemed to go to the next slide. But this is an event. It won't play it. So hopefully the other video clips I have will play. But this is a video clip of a person walking across an intersection. And it results in a critical or a near miss event. So the analytics that we have tracks those kinds of events for our customers. So we put these up at a location, and we can measure when these things happen. The critical question from an investment and management perspective is, how often are these events happening? And if you look in the lower left, that's the magic or the real value of conflict analytics, because we can observe a site over a week or a month or continuously and understand where the conflicts are happening, who's involved in those conflicts, how severe are those conflicts, and importantly, what should we do about reducing those numbers. Here's an example of one of our customers. So we collect this kind of information, and we can measure when vehicles are really close to each other. The way to think about this and understand this, it's really important because it is something that is a change of the way we think about risk. Crashes are deterministic. Every single person in this room can look at an image of a crash or a video of a crash and know with 100% certainty whether it was a crash or not. It's deterministic. It either is a crash or it's not a crash. With conflicts, it's a probabilistic relationship to crashes. So this was not a crash, but we know that if this particular conflict keeps happening, that it is more likely that this crash will occur over the next month, 6 months, year. And the fact that we can observe and identify those locations that repeatedly occur is what we use to manage risk. So we have to convert our thinking from a deterministic view of what a crash is to a probabilistic view. That we have information from these conflicts that a crash in the future is much more likely because this event is happening. So the customer in this case would use this information to make improvements at the site if this indeed is happening a lot. So key to any analytics platform is AI. And you heard from the previous speaker a lot of detail about how we build AI models. But AI models are core to understanding, measuring both conflicts and other things. So one of the things we discovered as a company, and I'm sure a lot of other people have discovered as well, even we can measure conflicts, but we can also measure a whole bunch of other things. Like we can measure how many users are at a site, at a location. Where are they going? How fast are they traveling? So how fast are e-scooters using? Where are e-scooters going? So we have a number of customers that now are concerned about e-scooters and how they're going to increase risk in the environment. Are pedestrians using the crossings that we've provided for them? Are they walking elsewhere? Another critical piece is that, and very valuable information, is that AI can tell us and break down all of the types of road users that are at a site. So we currently have 13 classes of road users that we deliver for our customers. And so they can understand things, well, how many pedestrians are using a location, or how many bicyclists are coming through, and when are they coming through a location. That's really valuable information to understand risk. So I'm going to conclude with a couple of case studies that show you this technology in action for customers who are trying to solve the same exact problem that you're trying to solve, which is how do we use better technology to reduce crashes. So this was an application in Canada, and the pain point for the customer was that they were having a lot of crashes on roundabouts. And so they wanted to use a better, and they didn't understand what was happening at the location. So they used video analytics to understand this. And so what you see in the upper left, and unfortunately you can't see in the photo, and from the upper left is the before case, and the right is the after case. What you can't see in the photo is in the upper left, the paint markings were really deteriorated in the beginning. So the treatment that they applied were putting in the markings that you see here. And what you see on the heat map is the change in the conflicts before they did the pavement improvement and after. And it turned out in that study they had a 72% reduction in rear end and angle approach conflicts by putting in that paint. So the customer had immediate information that they had almost a 70% reduction in likely crashes, future crashes, because of using this technology to understand the effect of that treatment they had done. Second case study is the city of Bellevue in Washington in the United States. The city of Bellevue had two elderly pedestrians enter a crosswalk about 9 months ago. The walk signal had turned, so they did not have enough time to get through the crosswalk before the traffic had a green signal. Unfortunately, both of these elderly pedestrians were hit and seriously injured in this crosswalk. So their pain point was, how do we detect this danger and mitigate it before we have that outcome, so we don't have that outcome? And so what we're doing with that customer now is we're using our video analytics in the real-time product to identify that risk, pedestrians caught in the pedestrian zone late, and talk to the traffic signal. So using our edge device in real time, we detect the danger, we talk to the traffic signal and say, hold the all red or allow extension of the pedestrian walk so we don't have those pedestrians injured. There are a whole bunch of use cases like that that we can deliver to customers. A third one I will show you, I've got two more, is again in a US state, they put in high visibility crosswalks. Okay, they're trying to invest in the safety of pedestrians. But the question they have, how effective is that treatment? So again, we get in with video analytics, measure the pedestrian-involved conflicts, near misses, before that paint treatment, and then go in after and measure the number of pedestrian-involved conflicts. And there was a 56% reduction in the number of pedestrians involved in conflicts from this simple treatment. The city now has applied for funding to roll out this treatment across the entire city on a week's worth of empirical information. I think Tarek had pointed out, and others, and yesterday, that the old way of doing business would have required us to wait to see if people got killed. And we would wait 6 months or 9 months before we would roll out that treatment because we don't know the impact of it. But using video analytics, we can figure that out in a week, and we can roll out effective safety treatments quickly. This is another way we get to that 50% reduction. All right, my last case study. This was a complex merge on a high-speed facility in Washington, D.C. And the customer wanted to understand how, if we put this treatment in to deal with this complicated merge, where we've had lots of rear-end crashes and sideswipe crashes, can we be confident that that has solved the problem? And what you'll see from top to bottom are 2 sites, before-after cases, significant reduction on the left-hand side one, and complete elimination of the conflicts on the right-hand side one. So, to wrap up, I think what I feel like I was charged to do is to suggest ways that Saudi Arabia can achieve a 50% reduction in crashes, given the bold vision that you've laid out in traffic safety. And I think there are 3 activities that video analytics can bring to you. One is understanding what's going wrong at these high-risk sites. Really going and using video analytics to tell you exactly what's happening. Because crash data can't tell you that. The second one is implementing some real-time countermeasure or improvements so we can detect things and risk as it unfolds and take actions to improve and mitigate that risk. And the last one is rapidly assessing the treatments that we put in place, so we know that they're effective and we can roll them out across the nation or across the city or wherever it might be. Thank you.
Thank you so much, Professor Simon. As we agreed, we're going to keep the questions to the last session. So we'll call on the 3rd speaker, Dr. Ala Al-Khamis, to give his speech. Thank you.
Assalamu alaikum. Good morning, everyone. Thank you for the introduction and for inviting me to give this talk in this conference. And
it will come now.
Let's wait for the slide. If you can share the slide deck. Just a quick disclaimer before I start. As you can see in my affiliation, I am wearing 2 hats. I work in the industry. I work for General Motors, and also I wear academic hat working for the academia at University of Toronto and Ontario Tech. The work presented in this slide mainly is about my activities in the academia due to the confidential nature of my work at General Motors. The talk will be focusing on describing the transformative rules of smart mobility technology in enhancing traffic safety. This is the outline of my talk. I will Yeah, I will start by describing the intersection of smart mobility and AI, focusing on AI as foundational technology of smart mobility, and also as a technology enabler to enhance the traffic safety. And also I will discuss some number of potential barriers that we need to handle in order to achieve the full potential of AI technology to enhance the safety. And also I will conclude with some key remarks at the end. Let me start by a very brief introduction to smart mobility. Smart mobility actually is a wide umbrella for different systems and services to meet different end user needs without compromising the collective good of the society and in the environment. These systems and services are built based on advanced technologies and also new business models such as circular economy, sharing economy, gig economy, servitization, and passenger economy. Example of existing and emerging systems include like circular industry 4.0, intelligent transportation system, and the move toward electrification, and also connected vehicle and assisted and automated mobility system, and also micromobility and urban air mobility, and also including air taxis. And as you can see in the slide, some example of existing and emerging services. Some of these services we are currently using, like for example, shared mobility and mobility as a service, first and last mile transportation, last mile delivery, and active mobility. All of these systems and services are trying to achieve or address different customer needs in terms of barrier-free mobility, seamless integration between different mobility modes, and also affordable mobility. And as Simon mentioned, most of this technology also can be an enabler to achieve Saudi Vision 2030. If we take an example, seamless integration, integrated mobility, if you enable seamless integration between different mobility modes, this can increase the percentage of the population using public transit from the current percentage of 1% to 15% as one of the target of Vision 2030. And also assisted and automated mobility, and also intelligent transportation system and smart intersection improves the safety and also can achieve one of the targets included in this vision to increase the number of autonomous driving vehicles by 15% by 2030. And also the move and the transition toward electrification is an enabler also to achieve the vision of having 20% of public transport to be electrified by 2030. In my recent book about smart mobility, foundational technology and wider impact, I listed number, or I tried to address what are the foundational technology and technology enablers and disruptors behind these emerging and existing smart mobility system and services. But I do believe that the widespread deployment and also the societal acceptance of such kind of technology will not depend only on the maturity of the technology, but also on the proper city planning to accommodate such kind of evolving technology, and also the availability of well-developed smart mobility governance that is moving target in reality. That's why smart mobility depends on a triad of complementary factors, technology, city planning, and governance. In this talk, I will be focusing mainly on technology, and I will address AI as one of the foundational technologies of smart mobility, as you can see in this slide. AI, as you know, is a kind of evolving, is one of the fastest growing field of technology, and has successfully delivered many commercial products that we are touching everybody's lives every day. And I define AI as an evolving technology. It is new technology, but it's fast evolving technology that try to mimic or reverse engineer the biological intelligence, but not only mimicking or reverse engineering the biological intelligence. This technology also has a potential to augment our biological intelligence by empowering us with gigahertz level of reasoning and learning capability, and the ability to discover hidden patterns in multidimensional data. So the AI as a technology is a technology that mimic or reverse engineer and augment the biological intelligence. That's why sometimes I like to have like the explanation of AI not as artificial intelligence but augmented intelligence. AI for me stands for augmented intelligence because it can boost our productivity and it can increase our intelligence. Same way when we use tools and robotic tools to increase and augment our muscle capabilities. So if we look at AI as a big picture of AI, we can summarize like three different patterns of use of AI. I've summarized them here as situational awareness. AI enable us to achieve situational awareness about the system and the process we are dealing with at different level of sites. I will talk about in the next slide. And also AI enable us to automate, and this automation can be to automate a physical process like automated driving, for example. It is a kind of automation of a physical process. Also, we can use AI to automate a digital process. For example, if you look at even human-machine interaction or voice like assistant or a chatbot is a kind of automation, and we are using it. Maybe you can provide roadside assistance through voice assistant, and also we can automate several other like digital process if we are using robotic process automation technology. AI also enable us to solve different complex problems. This problem can be design problem, planning problem, and control problem. And I will give you a few examples about the potential use of AI for optimization. And if you look at these three tasks, actually these three tasks behind anything smart. Because when we call something smart, smart means that it's the ability to optimize. And we cannot optimize some things that we cannot automate or control. And we cannot control some things that we cannot monitor. So we need to be aware about the system we are trying to optimize, and after that we do automation, and automation opens the door for us to optimize. Taking situation awareness as an example here, situation awareness or AI can enable different level of situation awareness from sensing to perception, to comprehension to even projection. So we can achieve different level of size by using the data. Many people say data is a new oil, which is true, but I think the information that you can generate out of this data is a valuable commodity akin of oil being refined to a useful product. So I think the value is more into the information that you can extract from the data. If you look at this vertical axis shows the value of the information you can generate out of the data you manage to collect, and the horizontal axis represents how difficult it is to generate such kind of data. And if you look here, I think raw data, it's interesting, but it value almost nothing. It doesn't have much of a value until you start to process it. And first step to process the raw data is to clean the data in order to handle different imperfection aspects like missing data, noisy data, etc. Once you have clean data, you have like higher value kind of data, but it's time to do analytics. The first level of analytics you can achieve if you have this data, and assuming that this data represents traffic crashes data, for example. So the first level, you can apply descriptive analytics in order to answer a question like what is going on, what happened. So descriptive analytics answer this question. And if we take the example of traffic accident data as a clean data, so this descriptive analytics can allow us, for example, to show the most common times of accidents, type of accidents, of vehicle involved, and the location, and also the hotspot of highest accident rates, which is a kind of more valuable than the traffic crash data by itself. And even though we can apply even higher level of analytics where we can answer the question about, for example, why did it happen? Why we are observing a hotspot in a specific area of the city with high accident rate? So this is what we call it diagnostic analytics. Diagnostic analytics can allow us to understand, for example, even the root cause of this hotspot. What would be the root cause of this hotspot? Whether it is a lighting condition because there is no enough lighting in this intersection, or maybe due to weather condition, or maybe due to bad road quality in this specific location of the city, or maybe due to driver behavior or other reasons. So the root cause of the problem that you are observing can be generated if you apply diagnostic analytics to answer the question, why did it happen? And if we go to even higher level of analytics, we can higher level of analytics can allow us to do what we call it like predictive analytics. Oops, sorry. Predictive analytics answers the question, what will happen? So now you observe hotspot in specific area of the city, you have some idea about the root cause of this problem, so you can even predict the likelihood of accident in this specific location over the time or under different weather conditions. So we can have a predictability or prediction capability to predict what's going to be happening in the future. So the predictive analytics module here can answer the question, what will happen? And if you apply even more advanced analytics, like we call it prescriptive analytics, you can come up with a very valuable kind of information in form of a recommendation to help the decision maker to take an action in order to mitigate risk of high accident rate in this specific location. And this recommendation can be, for example, to changing the traffic lights patterns, or maybe improving the road quality, or increasing public patrolling in this specific area of the city in order to reduce or mitigate any risk of accident. So as you can see here, we are taking from the raw data to clean data to the descriptive the information we are generating from descriptive analytics, and information we are generating from the diagnostic analytics and predictive can help us to answer the question, what we will do next in order to get the best results. In the context of traffic analysis here, this can be an opportunity for us to save lives and to avoid any risk of collisions. In terms of automation, the second pattern of use AI to automate, and as I mentioned, we can automate digital process, or you can automate physical process. Taken as like driving as a physical process, as an example, also AI is a major enabler to achieve different level of automation, from assisted driving to partial automation to conditional automation to high automation to full automation. And also, if we manage to reduce the complexity of operational design domain, we can deploy such kind of automated driving technology faster and safer, but in more kind of less complex domain, like for example agriculture domain. We have nowadays autonomous tractors, and also we have in mining and construction, because if you look at the environment like agriculture is much less challenging compared to urban mobility environment, because the environment is relatively highly structured, less dynamic, and maybe fully observable as well. And also in the near future, we will see the autonomous semi-truck and also self-driving shuttles. And we have a project actually in Dubai to deploy self-driving shuttles created by the company that's subsidized by GM, called Cruise Automation. And maybe in the next decades, I don't know exactly, we can achieve also higher level of full automation for personally owned autonomous vehicles. And also this can open the door to an economy called passenger economy, where the vehicle can be retrofitted or restructured or repurposed to be a mobile clinic, for example, or a mobile hotel, aside from being a mobility platform. The third pattern of use of AI, as I mentioned, is optimization. Optimization here, we can talk about different types of optimization problem, from design problems that require high quality of solution, but you have plenty of time to come up with such kind of solution. For example, if we want to find the optimal placements of charging stations in the city, the objective is to achieve highest quality of the solution, but you don't have the pressure of time. and also can have planning problem if you want to dispatch, for example, some fleet of emergency vehicle. Planning problem is restricted in terms of time compared to optimal placement of charging station in the city, and the control problems where we have a high level of constraints when it comes to time, and you may be able to accept less quality solution, but for the sake of having it running in real time. So we can solve all of this kind of problem, and we can also do spatio-temporal analytics for different subdomains of transportation, infrastructure, people mobility, and logistics. I have this kind of open source publication hub. I call it the AI for Smart Mobility, where I show different interesting projects about how to handle design, planning, and control problem in the area of smart mobility. And all of these projects are open source and supported by open source code. And also recently I published a book about optimization algorithm, where I show the potential application of graph search algorithm, meta-heuristic, and machine learning to handle different complex problems in this domain. Most of this material are available online for free and also supported by open source code written in Python, and also are using real data from the city because also this part of the course I teach at University of Toronto. Most of the data are about City of Toronto, but this doesn't mean that we cannot use the same code but just replace the data by data collected from a different geographical area, and the code will run without any problem. The problem, as I mentioned, tackling different aspects of infrastructure, people mobility, and also logistics. Taking automotive, because I work for automotive company as an example, where AI can be applied along the life cycle of vehicles, starting from designing the vehicle, we are applying AI. There are different opportunities where we can apply AI to design a mobility platform, like a vehicle, for example. We do generative design in order to save the time and also the budget to do physical prototyping, and also to optimize the design before we actually implement the design. And also we are applying AI in manufacturing and assembly plant, where we do it for balancing, for example, the assembly line plant, and also for quality assurance and test automation. During the operation of the vehicle, there are so many opportunities where we can create customer-facing feature based on the use of AI to create feature for diagnostic and prognostics, and also predictive HMI and personalization. And also during feedback and update, also AI is an enabler to achieve, for example, intelligent assistant agents or sentiment analysis. We are analyzing the claims coming or the warranty claims coming from the customer automatically nowadays, instead of spending too much time doing this process. And also we are providing or analyzing sentiment feedback by analyzing the data and the feedback coming from the user, whether it's inside the vehicle or outside the vehicle. And also we do a lot of work related to optimizing the incentives we are giving to the customer as a way to increase the sales and also to get the customer more engaged. And even during the disposal and recycling, there is many opportunities to use AI to achieve the concept of circular economy, where we can also predict the battery life and reduce the battery ownership cost, and also improve the battery recycling and also the AI sorting. Let's give a specific example for the AI as an enabler for traffic safety. And I will start by showing one major source of data, because as you know, AI, most of the current techniques of AI are kind of statistical, data-driven kind of techniques that require data. And data, actually, we are not lacking data. Even like a vehicle nowadays can generate from 4 to 20 terabyte of data every day based on the level of automation and the sensors you have in the vehicle. Another very interesting source of the data is connected mobility, where we have different pattern of communication between the vehicle and the external actors around the vehicle, starting from even the road users and also the occupant of the vehicle. There are many patterns of communication between the vehicle and the occupant, whether this occupant is driver or even passenger. And also we have vehicle-to-vehicle kind of communications that enable different AI-powered safety-related feature like post-crash warning and pre-crash warning. And also we have vehicle-to-infrastructure, where we can also do red light warning and also work zone warning and emergency vehicle signal and intersection collision warning. And even if you look at the vehicle-to network, also is another pattern of communication, where the communication between the vehicle and the infrastructure is not directly, but it is done through the network, where we can also use this kind of communication to enable service like mobility as a service and vehicle data as a service and in-vehicle payment methods. Sorry, I didn't move the slide.
Yes.
Yeah, this is the slide I was talking about.
Professor.
So there's different opportunities to create AI-empowered feature thanks to the vehicle to anything. Sometimes you call it the vehicle to everything, or V2X, where we have different patterns of communication between the vehicle and the external world, whether it is like occupant of the vehicle or the road users or the infrastructure or the network, where we can create or gather this data and create many customer-facing feature and many safety-related features. To give us more specific example, one potential application is a smart intersection, and I think Simon talked about this, where we have a number of sensors mounted in the intersection in order to enhance the safety of this intersection. And this kind of sensors can be LiDAR or can be camera, and also supported by mobile edge computing and also cloud edge computing and also wireless roadside units. So such a kind of smart intersection open doors to do a lot of tasks that is related to traffic safety, like traffic counting and trajectory classification, accurate speed measurements, and also detection of near misses and near and crash prevention. For example, this is an example of some projects in Ontario. The project on the left is about traffic counting and trajectory classification, and Ontario like online camera calibration is a project done between University of Toronto and York University. The project on the right is about traffic analysis. We have a smart intersection in Durham region, nearby Greater Toronto area, where we mount cameras, and also we use this for traffic analysis, and also we are using it to detect the jaywalker in order to be aware about the situation, and this also can lead to take some decision to improve the safety of the intersection. At University of Toronto also conducted some advanced research in the area of multi-agent reinforcement learning, where we do cooperative variable speed in mixed traffic scenario. Mixed traffic scenario when we can mix automated driving with human driving vehicle. And based on this algorithm, we managed to achieve superior performance in terms of throughput and average velocity, and also safety, avoiding crashes between the vehicle by adopting the concept of cooperative variable speed. The project on the right also is another paper we published this year about deep reinforcement learning to control the traffic signal timing, and also we compare this with traditional traffic signal timing and achieve higher throughput and also less congestion compared to the original fixed scheduling. Another project also we are focusing on is the idea of detecting road users, vulnerable road users. The road user actually can not restricted to pedestrian. It can include also jaywalkers, law enforcement officers, like a road construction worker. So it's very important also to improve the safety by detecting the crossing of those kind of users and also the intent of crossing. Even before the crossing is happening, we are trying to predict the intent, whether this user or pedestrian has intent to cross or not. And this can enable, for example, predictive HMI, where we can warn the driver if the vehicle is human-driven vehicle about to stop, or maybe this can be an opportunity to activate the automatic emergency braking if we are talking about self-driving vehicle.
Dr. Khan?
5 minutes? 2 minutes? Okay. So this is an example of a project we conducted at Ontario Tech. It's a kind of PhD research I supervise, where we use a vision transformer in order to predict the intent of the crossing, intent of the pedestrian cross before the event happens. And also, right now we are trying to replace a vision transformer by a new approach called geometric deep learning, where we can include a local and global context, including the nature of the crossing, whether it is market crossing, signalized versus unsignalized, and some other contextual information like lighting condition and weather condition. So I will end up my presentation by discussing some potential barrier we need to be aware and we try to handle in order to achieve full potential of such kind of emerging and interesting technology. First is adversarial and edge use cases that we need to deal with, and also the adversarial behavior that may be shown by a number of the pedestrian towards self-driving vehicles. And also another aspect is the learning over time. If we manage to create very efficient machine learning model, you have to take into consideration that the transportation is non-stationary kind of environment, so data keep evolving, and this can cause some sort of drift that the machine learning model need to keep learning in order to handle this drift. And also another concept is the domain adaptation. Even if you manage to create a machine learning model using, for example, transfer learning, that continually learning, we may face also as another challenge of adapting with the domain, especially if we are talking about the mismatch between like software life cycle and hardware life cycle. If you talk about AI, the AI is doubling its compute every 3.5 months, compared to the hardware life cycle that is doubling its compute or its capacity every 18 months according to the Moore's law. So we may be expecting some sort of mismatch between the capability of the software module and also the capability of the hardware module we have in the vehicle or in the telematic system that can prevent us from deploying more sophisticated model due to the cost or due to the lack of compatibility with the hardware. And also there are some other potential impacts, like the impact on human cognition, cybersecurity, data privacy, and equity and ownership. For the sake of time, this is just an example of some edge cases and adversarial use cases we are trying to deal with, including inclement weather condition. And also, there is many people are expecting that some people or some pedestrian may show bullying behavior toward the self-driving vehicle, especially if we are talking about zero-occupant vehicle, right? Vehicle is self-driven and nobody inside the vehicle, so maybe somebody can block the way in front of this vehicle, so we have to deal with such kind of bullying behavior. I recently published 3 patents to deal with such kind of situation by using like adversarial intent recognition capability and opportunity framework. Also, as you know, data is the food for the perception and decision-making modules we are using in the smart mobility technology. That's why it's very important to pay attention to data ownership, equity, and privacy, and to answer very related questions in order to build the trust.
Dr. Khamis, your time is almost, if you can round up. This is
last slide.
Okay,
last
good.
slide. Okay, last slide here is I just want to raise awareness about the need to have a smart, like a governance framework to deal with the different important aspects related to ethics and safety and security and privacy, compliance, bias, and performance and transparency to gain the trust in order to avoid a situation of confusing moon for traffic light or confusing a stop sign for maximum speed sign due to small adversarial attacks. This concludes my slide, and thank you for your attention.
Thank you, Dr. Khamis.
alert or haptic. But we have to keep in mind that the driver is still in control of the vehicle. There is no transfer of any driving skill, driving task from the driver to the vehicle. So in our experiment, our vehicle ITS station consists of three components: the HMI, the human machine interface, which is shown here in the left bottom figure, and antenna, and the communication and processing unit, which is shown in the right bottom feature. Okay, so how to, if we are going to conduct a CITS experiment, how we are going to assess the advantage? And of course, we assume there is advantage. So in order to assess the advantage of a function, of advantage function, so usually we run a field operation test. So what is field operation test? Field operation test is a study undertaken to evaluate a function or a set of functions under normal operating condition. And by normal operating condition, we mean that under the normal driving condition. So we test the function when our participant drive their vehicle in everyday routine. And usually field operation tests recruit hundreds of participants and it runs for few months to 2 years. And also, if you are conducting field operation tests, you have to follow a methodology, and we follow the European methodology, which is FISTA, and this methodology explains to the experimental every step they have to take, starting from defining the function, research question, research hypothesis, how to calculate the measurement and response, and what is the best modeling methodology to use. So now what we did in EBISwitch connected vehicle pilot. So ICVP enabled 6 V2I use safety functions, which are shown here. And at the same time, we tested another V2V use cases on a simulator because of technical difficulties we faced at this time. The ICVP covered 300 kilometers square of road network. We have connected 29 traffic lights. We recruited almost 350 participants, and we follow the European standard in our communications. What we need from this field operation test? So we have two main, let's say, research questions. The first research question: does CITS improve road safety? This is one important question, and the other question is about: is the system acceptable to drivers? Because if they didn't accept the system, they are not going to purchase it. We recruited our participants such that their distribution is very close to the gender and age distribution in Queensland, Australia. And we run our experiment using within subject design, where we assign participants randomly to 3 groups. The first group is treatment first, where they start the participants in this group start with HMI, the human machine interface, active, and then for the first 6 months, and then during the last 3 months, their HMI turn off, and the baseline first group start with HMI off, and then switch activate the HMI at the last 6 months, and then we have a control group which has HMI off during the 9 months, and because of ethics consideration and recommendation, actually we turn on the HMI only for the last 2 weeks. So how did we evaluate the safety? So simply, we come up with two hypotheses. The first hypothesis is that if you are HMI on, or if the system is active, we expect that when you face a critical safety situation and you receive a warning, you will have a lower mean speed. And we normalize this speed by the speed limit because we have different speed limits in our test bed. And also, we assume, another assumption is that HMI on participant has a lower acceleration. And acceleration, it's simply the integration of the absolute value of the acceleration over a long period of time. So how did we prepare and collect our data? Our data is collected in a form of trips, where every trip represent the data collected when a participant starts his engine until he turns off his engine. This is a trip. And after that, we process this data and we cut it into what we call scenario, where each scenario includes a safety critical situation. This safety critical situation could be roadwork, could be a signalized intersection, one of our connected signalized intersection. And also, because our methodology, we are following FISTA, which is event-based analysis methodology, so we have to come up with something called the analysis window. We are not going to analyze the whole scenario. If we analyze the whole scenario, any signal we are looking for, it will be diluted. So we have to come up with a shorter analysis window, and this analysis window shouldn't be too short, otherwise we will miss all the signal. So it's not so long and it's not so short. And because we are aware of this concept, trash in, trash out, so we did data filtering process where we started with all generated scenarios, then we remove all scenarios which doesn't have any warning, because we are looking for a difference when a warning happens. And for the ethical consideration, if we have the participant name on the scenario unknown, we remove this one. And also, we have a set of data quality flags, and based on these flags, we remove any scenario which seems to have a data quality problem. And this show you, this one shows you an example where we start in this use case. Actually, we use only in back of queue, we use only 19% of the collected data, and on the other case, if you look, only 4% of the generated data we used in order to come up with a good conclusion. And this slide shows the different techniques we used to filter the data based on quality, and this also shows you how many warning we get for each scenario. So our modeling methodology, we use the generalized linear mixed model plus bootstrapping because of the assumption. In most of the cases, we actually find that the data doesn't follow the assumption of this model. We also consider fixed effect, including the HMI mode, the HMI on and off, such that we can compare between the people who have the HMI on and off, and we have other related participant-related regressors and environment-related regressors. Also, we consider, because of the repeated measurement, we consider adding random effect to our model. So now this is an example of our analysis. So in this analysis of roadwork warning, we try two analysis windows, and as we can see, actually the result is promising. We see that there is decrease in the speed when you are approaching the work zone, and there is a decrease in speed in the work zone itself. The treatment acceleration, we find that there is an increase in the approach before entering into the work zone, and there is a decrease in the acceleration compared to the HMI off group in the event zone. Then it comes to, okay, so is higher acceleration value is a bad thing? No, it's actually not a bad thing if this is out of the conflict zone or out of the event zone. This means that the driver is actually aware and he take action before getting into the work zone or a conflict zone of intersection. So the second use case is the advanced red light, and in this analysis we focus only on the vehicle which is first in the queue, such that the driver has the freedom to run the red light if he wants. And again, we find that in the approaching the drivers approaching the intersection, signalize the intersection and receive the warning, we find that the approach with a slower speed and a better acceleration. So key finding, so we find that there is a significant lower speed and acceleration for most warning. We have 2 use cases. Actually, we didn't get enough data to analyze the data and find a significant result. And finally, we used Nelson power model to come up with an estimation in case of 100% penetration of connected vehicle, and we find that we have this. We have on average 10% reduction in fatalities if we have CITS at 100% penetration. The second question is about the acceptance of the system to the user, and actually we collected 4 questionnaires during the period of the experiment, and we have optional interview and optional focus group with the participant. The questionnaire focus on the attitude toward the ICPP, HMI, and warning, and other experience related to ICPP, experience with technology, and so many other things. Individual interview, this is optional. Our team interviewed 53 participants, and also we interviewed 14 groups, or conducted 14 groups of to actually come up with after we analyze the data, we find some weird findings. So actually this was our chance to ask a participant, okay, why did you behave like this? So this is the purpose of this focus group. Key finding, okay, all 3 user perception studies indicate that participants were positive about connected vehicle, so actually we find that which is weird, older adults have greater acceptance compared to younger adult, and the most positive feedback use cases, the ICV, the in-vehicle speed use case received the most positive experience by the participant. Also, a participant, they wish that they have a greater control over the system in terms of voice, how the warning displayed to them, and their main concern about the timing of the warning. Sometimes the timing of the warning is not accurate.
Dr. Mohammed, you have like 2 minutes.
I'm okay, I'm fine.
Okay.
So in conclusion, our finding is that there is a positive safety impact, and people are eager to purchase connected vehicles, And also, this actually suggests that future rollout of CITS technology will be well received by the public. Thank you.
Thank you, Dr. Mohammed. Now we have come to the end of the talks, but we have some few minutes for questions from the audience. Yes, the mic.
Yes, here.
We have a first question.
Okay, go ahead. Hi, everyone. Okay. This is Abdul Latif Al-Abid, Allah, Head of Traffic Safety in Al-Khubar. Thank you, everyone, for what you exactly present. It was a good presentation for everyone. Actually, I have a lot of questions, but maybe because of the times, I just want to ask Prof. Simon. Regarding what you mentioned about Saudi Arabia, that we already had to solve the problem regarding to the car accident. And you said that's the main target for us, just also only solving the problem. Actually, we have a council from each ministry in Saudi Arabia, from the Interior Ministry, from also Health Ministry, Road Ministry, that usually we collaborate together to know exactly about how the accident happened, and then after that we try to find the problem for that, we solve the problem. Regarding also, we usually focus about the black spots. We know exactly what is the black spot, and we deal how to solve the black spot, and we'll try also finish it and continue monitoring about the solving for this problem. This is the first things that I need you to update your knowledge regarding to our system. And we usually predict the car accident before it's happened. That's also our rules. Traffic police usually in every type or every region in Saudi Arabia, they have also a private counsel. They usually finish their case and also solve their black spot and continue also for monitoring in it until it's not happen. And the second question that you said, usually you put for some intersections that some camera for monitoring the bad behavior or something from using that, predicting the car accident. Did you study about the road user behavior instead of just put camera in any instruction and you predict the car accident? And also, when you just said that you're gonna solve the problem for the intersections, that means there is other intersection doesn't have any camera, so we cannot know exactly how to predict the car accident there. This is my question, and thank you for your time.
Thank you so much.
Great to hear all the great things that you're doing in Saudi Arabia to address the road safety problem. I'm aware that all of our customers manage and maintain their list of hotspot locations and are going in there. The constant feedback that I hear from our customers is that they often lack the detailed information to understand exactly what to do to fix some of those locations. And the video analytics helps in that piece. So that's where the video analytics comes in for that piece. But it's great to hear that the wonderful things that you're doing in Saudi Arabia. And I didn't mean to imply that you weren't doing great things. The fact that you've set a target to reduce crashes by 50% is a testament to where Saudi Arabia has positioned itself in this effort. So to be applauded. Your second question, the behavior piece is something that we try to capture with compliance with speeds, compliance with the pedestrian, activation of signals and other things like that. So we capture it and we provide it back to the customers to decide what to do about that behavioral compliance or non-compliance. Wrong way driving, speeding, red light running, those kinds of behavioral non-compliance. We measure it we don't measure, we don't understand why they're not complying, but we can measure, their compliance rates at various locations. I think your last point was intersections that don't have cameras. Often our customers will put up temporary cameras if they feel like they need to understand what's happening at a site that don't have cameras, and they'll use mobile cameras or other, what means to install a camera at places where they don't currently have, infrastructure.
Thank you so much, Professor Simon. If I would like to add from what he said, maybe the second question, he talks about challenge regarding 2 locations that do not have cameras. So we have a vast network of roads, and how is it, is there any sustainable way of, positioning this to maximize the outcome of video analytics for prediction and all of that? You can add that to that one.
So what a number of our customers will do will invest in mobile camera units that they rotate.
Mobile cameras?
Yeah, mobile.
Okay.
So they'll install them and put them in for a temporary case to monitor locations that they don't have permanent cameras.
Okay, thank you so much. Okay. Go ahead.
Yes, can I add a comment on this issue? Because the problem of placing cameras everywhere in the network is a perspective, but it is not what we have also. It is because we are proposing a mixed system where you can merge the camera data in a specific.
It's on.
Close. Okay, sorry. I'm talking about the opportunity to mix the checking of vehicle with onboard sensors with the camera in fixed position. That give more opportunities for screening the overall network and with more detailed information in critical intersection or location where the data from the onboard vehicle can be fused with the data from cameras. But that is our approach, that we can use both onboard system and camera visions in the road network in smart cities, but also outside the cities.
Thank you so much, Professor Cafiso. The next question?
Can I add something?
Oh, okay.
Just a quick, okay.
Go ahead.
Yeah, just a quick comment here. Like at the City of Toronto, actually, we have open data repo, and we are doing the driver behavior based on the historical record, where we can identify the hotspot, where we can install such kind of cameras. And also we have a system called automated patrolling units that are kind of not fixed camera, but mobile units that will move it from like every 3 or 6 months in order to analyze the driver behavior in different parts of the city. So not all of the cameras are kind of fixed. We are mixing fixed with mobile units that are moved every 3 to 6 months.
Thank you so much, Dr. Ola. So the second question, sir.
Assalamu alaikum. Dr. Ibrahim Dbeib, the chairman of the Aman Society for Prevention of Traffic Accidents in Riyadh. My question goes to Dr. Simon. I wonder, from engineering perspective, can we use your technology to study different alternatives of the proposed profile or the road, the geometry of the road, to predict the future accidents and black spots, to select, amongst other criteria, the best alternative on the proposed profiles? Thank you.
That's a fantastic question. And there's several of our customers that are grappling with the decision context that you just described. That is, there are a number of different treatment solutions for a given road segment or intersection or roundabout or whatever it is. And what our customers want to know is they come to us for is to give us evidence to help us decide which kind of infrastructure is the safest and is the safest way to operate. And that's one of the best things about video analytics, is that you can give that evidence very quickly, and a customer can trial different things. At the Bellevue example was a perfect one. They weren't sure how to make pedestrians safer, and they used the painting treatment to understand better, and we were able to tell them very quickly that that treatment was very effective. But yes, the answer is yes, you can use it for that. Yeah.
Okay, thank you. Unfortunately, due to time constraint, you can interact with the speakers after this session. You can have all the time and discuss with them. So we will end the session now, and thank you so much all for listening. Thank you.
شكرا لرئيس الجلسة والمتحدثين في المحور الثالث، والذي كان تحت عنوان التحديات المتعلقة بالذكاء الاصطناعي عند تطبيقها في السلامة على الطرق. والآن اسمحوا لي أن أدعو سعادة العميد أحمد السريحي مدير مرور جدة لتكريم رئيس الجلسة والمتحدثين لهذا المحور، فليتفضل مشكورا. نبدأ برئيس الجلسة الدكتور محمد طلحة، جامعة الإمام عبد الرحمن بن فيصل. دكتور علاء خميس، جنرال موتورز كندا. دكتور سلفاتور كفيس. بروفيسور سايمون واشنطن. وأخيراً الدكتور محمد الحناوي. صورة جماعية لرئيس الجلسة والمتحدثين مع سعادة العميد. جروب فوتو بليز. شكرا حضورنا الكريم. سنتوقف لاستراحة قصيرة قبل أن نبدأ المحور الرابع بإذن الله تعالى، والسلام عليكم ورحمة الله وبركاته.
Professor Kafiso, welcome to the stage.
بسم الله بسم الله بسم الله الرحمن الرحيم. بسم الله بسم الله بسم الله الرحمن الرحيم. بسم الله بسم الله بسم الله الرحمن الرحيم. بسم الله بسم الله الرحمن الرحيم. تستمعين بسم الله بسم الله الرحمن الرحيم. بسم الله بسم الله الرحمن الرحيم. تستمعين بسم الله بسم الله الرحمن الرحيم. تستمعين بسم الله بسم الله الرحمن الرحيم. تست مايك. بسم الله. من السماعة نفسها. بسم الله الرحمن الرحيم. تست مايك. بسم الله. بسم الله الرحمن الرحيم. تست مايك. بسم الله. بسم الله الرحمن الرحيم. تست مايك. بسم الله. بسم الله. بسم الله الرحمن الرحيم. تست مايك. بسم الله. بسم الله الرحمن الرحيم. بسم الله الرحمن الرحيم. تست مايك. بسم الله. بسم الله الرحمن الرحيم. بسم الله الرحمن الرحيم. بسم الله الرحمن الرحيم. تست مايك. بسم الله. بسم الله الرحمن الرحيم. تست مايك. بسم الله. بسم الله. بسم الله الرحمن الرحيم. تست مايك. بسم الله. بسم الله. بسم الله الرحمن الرحيم. تست مايك. بسم الله. بسم الله. بسم الله الرحمن الرحيم. تست مايك. بسم الله. بسم الله الرحمن الرحيم. تست مايك. بسم الله. تشيك مايك. بسم الله الرحمن الرحيم. تست مايك. بسم الله. بسم الله الرحمن الرحيم. تست مايك. بسم الله. تشيك مايك. بسم الله الرحمن الرحيم. تست مايك. بسم الله. 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 بسم الله الرحمن الرحيم. تست مايك. بسم الله الرحمن الرحيم. تست مايك. بسم الله. بسم الله. بسم الله. بسم الله.
الهلال الأحمر السعودي معك ضياء.
بسم الله الرحمن الرحيم. بسم الله تستمعك. بسم الله الرحمن الرحيم. بسم الله. بسم الله الرحمن الرحيم. تستمعك. بسم الله. بسم الله الرحمن الرحيم. تستمعك. بسم الله. لسه. بسم الله الرحمن الرحيم. تستمعك. بسم الله. بسم الله الرحمن الرحيم. تستمعك. بسم الله. بسم الله. بسم الله الرحمن الرحيم. بسم الله. بسم الله الرحمن الرحيم. تستمع. 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 بسم الله. بسم الله الرحمن الرحيم. بسم الله الرحمن الرحيم. تستمع. بسم الله. بسم الله. بسم الله الرحمن الرحيم. تستمع. بسم الله. بسم الله الرحمن الرحيم. تستمع. بسم الله. تستمع. بسم الله الرحمن الرحيم. تستمع. بسم الله. بسم الله الرحمن الرحيم. تستمع. بسم الله. بسم الله الرحمن الرحيم. تستمع. بسم الله. بسم الله. تستمع. 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 تست.